Hello everyone, Dr. Shane back with another pre-lab video for Chemistry 125. Okay, so there's a lot of pre-lab questions on the board, and I divided them up into two sets, kind of warm-up problems on the right side, and we'll use some of those same numbers, no need to reinvent the wheel, on the left side. So the point here is, if you can come into lab with as many of the dry lab calculations on the left side done as possible, then your calculations for this lab will be very, very straightforward. And I gave you dry lab data that should give you an answer close to the answer you're looking for, which is 22.4 liters per mole. And I'm gonna come out in front and explain these a little bit more if you need it, but if you wanna stop the video and simply copy things down, or just, I don't know, take a freeze frame picture and then do the questions later. Whatever you do to keep track of the questions is fine. Okay, here we go. Oh, also we may take a little field trip here with the end of the video, so it may be kind of bizarre at the end, but I'll get to that later. Okay, so you can write all this down. So we're just going to do some warm-up questions here. Let's assume you go and you measure barometric pressure. I'm going to show you what a Mercury Barometer looks like. You can look one up online. We have one actually in the stock room, so I'm going to take you back there and show you that later. But let's assume you go back to the barometer and you record barometric pressure in the room today, which you should do before you do any lab that involves pressure. And you record a reading of 746.2 mmHg, millimeters of mercury. The units are vital in this experiment. Not just the units of length or volume, but is it water or is it mercury comes into play. That's very important to remember that. And let's just assume an easy temperature of 20.0 degrees C. That's a little warmer than it is usually in this lab. Okay, first thing is, go to your textbook and you can type in vapor pressure of water and a table should pop up. Or you could Google it or search it, whatever, and we're going to have some tables here for you. It shouldn't be hard information to find. So look up the corresponding vapor pressure of water at 20 degrees Celsius. So, and the units that you get, I don't know what units you're going to get. Depends on what table you look at. So what you're going to want to do is look that up and convert it to the same units of mmHg, or convert mmHg to the units that you look up in the table. Okay. That's fine. So look that up, get that answer, and then do this problem. And this is the law of partial pressures. So gases are often stored or collected over water. An example of this is in a hospital. Sometimes if oxygen is used, there's water present as well. It kind of helps also purify the gas, but that's not something we're going to get into now. Well, let's assume that you collect a sample of gas. It doesn't matter what it is, because these are all ideal gases. So usually in the gaseous state it will matter under the conditions we talked about. So let's assume you collect it over water. So determine use the law of partial pressure to determine the pressure of the gas by itself. So the law of partial pressures basically says the total pressure is the sum of all the individual gases. So here we have the total pressure is the sum of two gases. So it's a pretty easy problem. Just make sure your units match up. And then just for a little practical things, whenever you do this video, look up on your phone or computer or whatever, look up today's barometric pressure in Shippensburg and then in Denver. And then make sure they're both the same units, of course, and then just explain why they're the same, they're different, one's higher, one's lower, okay, something like that. And the last one, I just kind of tossed this in here. There are three gas laws, and a better phrase really is gas equations. There's the ideal gas law, PV equals nRT. The combined gas law, P1 V1 over N1 T1, sometimes instead of ones it's I's, okay, equals P2 T2 over N2 T2, again, F's, I's and F's, ones and twos. That's called the combined gas law, and then the law of partial pressures. I think it's good that you understand, when do you use those? Under what circumstances do you use the ideal gas law, the combined gas law, and the law of partial pressures? That's kind of just a generic question. Don't spend a ton of time on that, excuse me, but that's a good one. And so those are the warm-up pre-lab questions. Over here I have a set of data that you can use to do dry lab calculations. And I'm going to refer to these when I do the experiment, but 1 through 4 are just mimicking the calculation section in your laboratory. Okay, let's go ahead and show you how to set up the experiment. It's very straightforward, and I'll kind of bounce back and forth between this. And I made a generic picture of this apparatus just to give you a visual, but I'm actually just going to show it to you. So let's go ahead and get started. And this is pretty quick. So the diagram in the manual is quite good. So here we go. I have 2 options for you here. Oh yes, I should say, when you come into the lab, one of the first things you should do is get your beaker of water ready. This is probably a bigger beaker than you have. And set that out, because you're just going to use tap water here. There's no reason to use deionized water here. You'll use deionized water here, but not in the beaker. So it's a good idea to let that sit out at room temperature, because when it comes out of the tap, it's colder than that. And that could have a small effect on your assumption that the temperature of the room is whatever your thermometer is. Okay, so we have 2 different udiometers here. One is actually a full-blown udiometer with a closed end, and the marks go top down, so we'll probably have this version out for you. But it doesn't really matter. We could also use a burette, as long as that's the stopcock open. As long as the stopcock is closed, it serves as a udiometer. We just need a closed, sealed tube with one end with marks on it. That's all we need. So I'm going to use this udiometer just for argument's sake. Okay, so how do you get this apparatus set up? So the first thing you need, and I'm going to show you some hopefully bad examples today. So as with all your observations, you always do before, during, after. So what do the reagents look like before? What do they look like during a chemical reaction? And what do things look like after? So make sure, so here's a piece of magnesium. And you can see that there's some mistakes I'm going to make there. That is, I don't know if you can see it on the screen. That is not pure magnesium. There is some oxidation on the outside. That would be a bad example. That would be a source of error. So we're going to give you probably better pieces of magnesium. So that's a bad example. So you would write that down. Okay, so you're taking a piece of magnesium, and this is just hard to put into a static handout. You'll have these rubber stoppers. One hole, rubber stopper, has to have a hole in it, or else it'll just pop out from the gas pressure. And it's got wires through it, and you want to take the magnesium and kind of bend it around the wire so it's going to stay in the bottom of the udiometer. Don't go too aggressive with bending and twisting it, because you'll break it, just like if you take a piece of wire and bend it back and forth. I don't know if that's going to work. It'll probably work. If the magnesium breaks off during the reaction, that's okay, because it should not matter, but I don't want to give that away. And then this will end up fitting, and make sure that fits in there snugly before you do anything else. So the idea is we're going to put HCl in here, and it's going to diffuse down, and then it'll start reacting. It's actually a pretty cool reaction. It's really interesting to see, and it's really fast. It only takes a couple minutes. I forget if I think we're doing 2 trials. Okay, well, whatever. It doesn't matter. I'm just showing you this once. So you've weighed the magnesium. You've taken all your other data. Oh, yeah, and I gave you slightly different data. I'll get to this. So that's ready to go. And let me just show you the mechanics before I put the HCl in. So you'll have your beaker of water here. You'll have your HCl carefully poured down here, and that's 6 molar HCl. That's half as concentrated as we get it, maximal concentration. So be careful, but you're not going to come into contact with it because you're going to add deionized water the whole way, even so it overflows. It's not going to mix right away. So just be careful there. So you'll add enough water so that it kind of overflows. You don't want any air bubbles. You'll insert this. You'll put your finger over the top. You'll invert it underneath the level of the water here, and then you'll clamp it. So that's sort of the mechanics of how you're going to set this up. And then you'll actually see the HCl diffusing down. I'm doing this because it's a refractive index change. So it'll look like swirls. Well, that's a refractive index change because the density of the HCl and the density of the water are different. And you'll actually see it diffuse down and then start to react. So let me just set it up and show you. And I'll probably do some sloppy things just to make a point. Okay, the procedure says that you're going to pipette 10.00 milliliters of 6 molar HCl. So first things first, you always record the molarities, and I really shouldn't be holding this up in the air like this. It's not safe holding it like that. You should always record the molarities directly from the bottle. Do not assume what's in the lab manual when it says, I think, 6 molar or 6.0 molar. There's more significant figures on the bottle, oftentimes, than in the lab manual, so make sure you do that. And instead of a pipette, because I want to save time, rather you sit here and watch me pipette, I just put some HCl into a 10 milliliter graduated cylinder. So we may end up using these because it's a little bit easier to handle, especially with 6 molar HCl, but I'll let your instructor handle that. The point is, we want to get some HCl down in here. And I actually do not, maybe some of you can see that, I'm not putting 10 milliliters in here, I'm just putting a sample in. And up here for this dry lab, I only have you put 8 milliliters in, just so you're not doing the exact same thing for your pre-lab. Okay, so we want to pour that into here and then add deionized water. So I'm going to get the deionized water now into a beaker. And again, you're going to want to overflow it so it's almost purposefully being a little sloppy. And deionized water. And I didn't think about this. When I'm taking the deionized water out of the spigot here, this is actually a little colder than room temperature. You won't have that problem in here. And when I say in here, I'm actually not in your lab, I'm in the other lab. So we've got that ready. We've got the magnesium ready. Everything's been weighed. We can get all the other data later. Okay, we're ready to go. So here's the acid. I'm going to pour that carefully. And I should say, if you get some droplets on the outside, like say a drop comes down and gets on your hand, it's not gonna like sting or anything right away unless you have a cut. Just make sure that you go wash your hands. So the acid's down here. You can always double check it's there. Okay, that's fine. Now you want to add the water. And you can use your wash bottle, but that'll take a while. That'll probably mix the acid a little faster. And you want to go the whole way to the top. Even overflow a little bit, that's okay. That's mainly water that's coming out of there. And then put your stopper in, check to make sure there are no air bubbles, because when I invert this, you'll have an air bubble go up, and that's a source of error. I don't think I have any air bubbles. I was kind of hoping to show you a bad example. So the acid's still down here, and it's a little wet on the outside, but that's okay. So we invert this, clamp it, and make sure that the level of the water I don't know if you can see this. It's swirling, it's kind of mixing as it goes down. Maybe while it's reacting, I'll come out from behind the camera and see if I can zoom in on that a little bit. You can probably fast forward this if you want to. Yeah, you can't really see it. Oh, you can. Can you see that? I saw some swirling going on there. Again, you can fast forward this part of the video. It's not like it's helping you with the pre-lab. I thought it'd be interesting to show you one of the reactions. I hope it works. Yeah, I'm starting to see some small bubbles form there. I don't know if you can see those, but those bubbles are hydrogen gas. Yeah, there we go, that's not bad. Nice thing about the camera. So that's hydrogen gas being given off. I think you get the point. So the hydrogen gas will then be collected in the tube, and every time a milliliter of gas is produced, in principle, a milliliter of water will be pushed out. So the space that's left behind will be primarily hydrogen gas, but also water vapor. Okay, I think you get the point. So wow, it's reacting pretty fast, no problem. And let me back it up now. Whoa, sorry about that. Back it up. Okay, while it's reacting, I'll just make a few more comments and hints about how to help you out with the calculations. I think that's, sorry, I'm probably not zoomed very well there. Fine, so let's fast forward in time. There's some gas collecting up here. The reaction's going pretty vigorously. Of course, you write all of this down. If you notice any leaks down here, then you want to write that down. I think that's actually a post-lab question. If water's leaking out of here, and so it's not from the pressure of the gas, it's the leak. All right, so I think we can push this off to the side. It's kind of cool looking, and maybe I'll pull it back in later. So don't you do this, but I'm just going to carefully slide this off to the side. And I really doubt that the way this uniometer looks when it's done is going to look exactly like this picture. I think I can safely degoggle from this distance. Okay, so you've got the warm-up pre-lab questions. And over here, you're given some data. You have a piece of magnesium. You've recorded its mass. For the pre-lab, just assume that the molarity of the acid is 6.0 molar, so 2 sig figs. And instead of 10 milliliters, you're going to use 8 milliliters. So when you do the lab, you use your sig figs and the concentration off the bottle. So don't use these data. We'll keep the atmospheric pressure the same. We'll keep the temperature the same. And two other pieces of data you will need is what's the volume of gas that's collected in here. And that's a volume, so it will be milliliters. Let's just assume it's 29.60. These burettes are 50 milliliter uniometers, or burettes, 50 milliliters. So that's a reasonable volume. And let's also assume that the height of the water, now this is a little tricky to measure. You actually physically get out a ruler and don't adjust the height of your uniometer once you have it set, just let it sit there. Take your ruler and record from the top of the water in the beaker to the top of the water left over in the uniometer and measure that. Now let's assume that this particular student measured a 7.5 centimeter height. Convert that to milliliters, that's easy. And also, it's important, this is not mercury. So if you convert that to millimeters, it's not 750 millimeters of mercury. It's 750 millimeters of water. Okay, so before we go to the calculations, I want you to think about this conceptually. If you have a column of water, okay, the density of water is about 1. And it has a certain pressure associated with it. What would be the equivalent column of water if it was mercury, where the density of mercury is 13 point something or other? And you'll have to look that up under the temperature. Well, it's going to be a lot smaller. So the equivalent mmHg is going to be much, much, much smaller than this of water. And you're using a ratio of densities. I'm not going to explain that too much, but you know you're doing it right if your mmH2O calculates to a very small mmHg. That is a very small number. That'll be a very small correction factor. So that's kind of my hint there. Oh, we're done. So there we go. So you'll measure from the top of the water to the top of the water in the beaker to the top of the water in the uniometer, and then you'll measure the volume here. So you're good to go. Probably most instructors, it's not important that you get all the pre-lab calculations perfect before you come to lab, but if you do, then you're set. So the first calculation, and this mimics, I think, what's in the lab. So first thing is calculate the pressure of the liquid water, just like I was explaining, in mmHg, using the formula that has densities there. And you'll need the densities of water and mercury at 20 degrees Celsius, and I think we'll look those up in lab. Then you use the law of partial pressures, to calculate the pressure of the gas. The gas, in this case, is H2, hydrogen gas. Fine. Then oh, by the way, these calculations do not necessarily, it's not like you use the answer for 1 to do 2, the answer for 2 to do 3, the answer for 3 to do 4. So don't look at it that way. In fact, I think 1, 2, and 3 are separate calculations, and 4 kind of combines it all together. I think that's on you to figure that out. Okay, then you calculate the moles of hydrogen gas using stoichiometry. You're given a chemical equation. It's pretty easy. It's magnesium plus HCl produces, etc., etc. So figure out how many moles of H2 gas using stoichiometry. And you'll have a mass and a volume and a molarity. So you should know how to do that. And then the last step is to calculate the molar volume. Now, there's actually a lot built into that last calculation, because you're calculating this at standard temperature and pressure. Standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere. So you have to use this, and I'm not going to go through that. That's kind of on you, using what you know in lecture, to figure out all those pieces together, is to calculate what's called the molar volume of hydrogen at STP. And the answer should be, even with the pre-lab data, I think, in the ballpark of 22.4 liters per mole. The units are important, so you want liters in the numerator and moles of hydrogen gas in the denominators. That gives you a clue of how to do the calculation. Okay, I think that's it. Get as far as you can here. That'll make the calculations for the lab pretty straightforward. And last thing I do want to show you, this is going to be kind of awkward, is I'm going to carry the camera back to the stock room so you can see the barometer, because it's kind of cool. So just come along for the ride. I have no idea how this is going to work. So I've actually got to pick up the whole tripod here. If we have small groups, we might be able to bring you back here. So I didn't plan this out very well. So this is our mercury barometer right here. There is a pool of mercury. That is a pool of mercury. I think I can probably show you this. Whoa, maybe not. Okay, well anyway. That is liquid mercury down in the bottom. And there's a glass tube in here that's open to the atmosphere. And the mercury, there's a thermometer just so you have convenience. And the mercury appears, whoa, sorry. You can read the level of the mercury over in this little window. Now, only part of this is open to the atmosphere because we expect the gas pressure to be somewhere around 760 millimeters. So what we do is we actually take, well, sorry, I didn't really think about this very much. There's a little dial right there that adjusts that metal piece up and down. And we adjust that metal piece so that it touches the top of the column of mercury, which is right in there. It's inside of, this whole metal thing is here just to protect it, because if this thing fell on the floor and broke, there'd be mercury everywhere, which is terrible. So then we physically measure the height of the mercury from the, well, you can't see it because of the plastic bin, from the top of the mercury all the way through this tube, and you can take my word for it, this is about 3/4 of a yard, which would be about 760 millimeters. But we're about 500 feet above sea level in Shippensburg, so we're not going to be at 760 on most days. We're going to be a little less than that. And then that's how we measure it. So that's a mercury barometer. If you want to look up something cool, you can look up water barometer and look at how high a water barometer would have to be. There's an interesting one on the Thames River in outside of London that's about a couple of stories high. And it's a nice artistic piece. Okay, so that's it. Long video, but some of that was hopefully interesting and useful to you. We'll see you in lab.